Okay. So for a relation, it is made up of a schema. That's this part here. The schema is the name and type. I'm not putting the type here, but I'll be better about that in the future. Each row of the table here, you can write it with these angle brackets. That is indicative of a tuple or a vector. And here you could say that the second coordinate of this vector is the name John. This is another tuple vector point. I can also call it. A point is looking at this as sort of a set, where, this is one point or one element in the set. And so then here would be another point that also has values for each of the 3 dimensions of the relation. And fine. So that's what a relation is. And the algebra of relations, that is the operations that you can perform on them. There's only 7 basic operations. There's more operations that exist, but you can achieve anything you want with these 7 basic relations, or these 7 basic operations. And so, for example, if you have, sorry about that. Let's try to move things around here. Okay. So, like with numbers, you have a plus symbol for addition, you have a minus symbol for subtraction, you have a slash for division, an X for multiplication, whatever. These are symbols that represent operations that you can do between numbers. And that's the algebra of the algebraic numbers. With relations, it has its own set of operations. And because these relations work more akin to sets than they do numbers, then there's a lot of overlap between the operations used for sets and the operations used for relations. The first 3 are the most like sets, I guess. There's the union. That's taking 2 relations, and any entry that appears in either relation will get combined into one relation. That's akin to addition. But it has a different symbol, this U, or the cup, actually. And then the intersection and the set difference. So all of these are sort of set operations. I think we've covered enough about that the last class. I'll remind you that for the union and intersection, set difference, all of these, the relations have to be of the same kind. What that means is that the schema has to be the same. So the same number of columns, same names, same types. Okay. Then we talked about multiplication, and multiplication in sets or with relations is called the cross product. And this is really just finding all possible pairings. So we discussed that last time. I won't go into it again, but of all of the operations, this is maybe a more complicated one. Still not too bad. Projection. Projection is a way to go from many dimensions to fewer dimensions. And so this just means eliminating a column. So here's an employee relation that has a name, age, and parking lot. And if we don't care about the parking lot, we can project it and get a relation with just the name and the age. So that's projection. It's akin to deleting an entire column. The select eliminates rows. So it eliminates entries. It looks, there is some Boolean here. This is a predicate, actually. A predicate is a statement that evaluates to true or false. So the select operation will look at every single row of a tuple and apply some predicate to it. It will have a statement and it will say, for this row, is this statement true or false? If it's true, then that row gets added to the list of results. If it's false, it gets passed over or skipped or filtered out. And that's the select. And the rename is really straightforward. That is just renaming a column. So, yeah, if you want to change the name of a particular column, then that's the rename operation. And that's it. Those are the 7. Those are the 7 basic operations for the algebra of relations. Before I go on and talk again about the natural join, are there any questions about these existing 7? About these first 7? Take that as a no. Okay. Then, okay, I'll go into my thing on joins again. Some of you might have taken MIS before or have previous experience writing SQL, or you might be familiar with the concept of joins. There's different flavors of join. There's a natural join, inner join, outer join, left join, right join. Different flavors of joins. They're none of them too complicated. But another thing is that the joins are we're going to avoid directly using joins in this class. Okay, so you can say it's a join, but then you actually have to break down the join into its parts. So the way that a join works is when you have multiple relations, so multiple tables, let's say 2 tables, and you want to combine these 2 tables together to form another table, such that there's 2 things. The number of columns in the result should be the combination of the columns of the 2 relations. And any row that exists in the result should be in reference to entries that exist both in table A and in table B. So here, for example, we have 2 tables A and B. Only the name John appears in both tables, and therefore it is the only entry that is that exists in the result. In addition to that, the result has 3 attributes. That's name, age, and operating system. So joins are very, very common. They're used a lot, and maybe some of you already have some experiences with them. Okay. I hope the idea of this natural join makes sense. If not, please ask me to clarify. But I'll say, again, for this course, we will not be using this bow tie, that symbol, because joins are redundant. You can do joins using some combination of the, I'll call them lower level operations, or lower level, operations. So the reason for this is because, one, I think that although, well, my experience is that a lot of students use joins without actually knowing exactly how they work. And they seem something like magic. And when something seems like magic, and you don't really know what's going on and you try to use it, you're prone to make mistakes. So that's one reason why we're going to go the longer way, so that it demystifies what is actually happening with a join. The other thing is that this is the way that things actually work. When you use a join, that is actually being processed as a sequence of lower level operations. And so you'll actually know what's happening kind of behind the scenes when you're doing a join. The last thing is that I think that it can help internalize the cost of doing a join. In particular, that one of the steps is doing a cross multiplication. And cross multiplication is really expensive. I'll talk a little bit more about that in a minute. But this is where we left off last time, and I left it as a sort of homework exercise. How can, given relations, these relations A and B, how can we arrive at this result using just the operations, just the 7 operations that we discussed? Let me pause and see if there's any questions, or if anybody was able to come up with how to break down a natural join into constituents of smaller operations. Okay, then I'll just start picking out on people. How about Alan? Yeah, Mike?
Yeah, can you hear me? Hello? Hello?
I see the mic thing going, but I'm not hearing anything. Oh, I'm sorry. I know what I did. Sorry, I haven't hooked up my headset. Just a minute.
Okay.
Stupid. There.
Can you hear me?
Ah, okay. Yeah, so
Okay.
So it was using my computer mic before. Sorry about that.
No
Okay,
worries.
great. So, Do you understand the question?
No, can you just repeat it one more time? Sorry.
Sure. So, do you understand the way uh, what a natural join is? Do you understand what a natural join is?
Uh, yeah, I mean, I guess so. Like to not that much, but yeah, I think I got the idea.
Okay. So instead of just writing this symbol here, this bow tie symbol, we are going to have a longer expression that can get us from these relations A and B. It can get us the same result here on the right, except that we're only using these things: rename, select, project, cross product, set difference, intersection, union. So how can we achieve the same result without using this bow tie, just using the other operations? So we're partly there now, and I'll show this part here. So here below, there's already two operations that we've done. Here's a rename, and then a cross product. And the result of that is this table here. Okay, so first of all, the reason for the cross product is because things that survive the natural join should be entries that exist both in table A and in table B. So if you find all possible pairings between relations A and B, then one, you get any possible combinations between the two. And number two, you get all of the information that's in table A. Table A has a name and an age, and B has a name and an OS. And so in one relation, you get all of that put together. So all of the information in table B and all of the information in table A get combined together via the cross multiply. The renaming is so that this column name, the first column name from table A, can be differentiated from the name column in table B. So that's why we do the rename. Okay.
So would you want to use like a set difference or something to like remove that name too? I don't know how you would remove that.
So you want to remove this name too, column?
Yeah, I mean, if we want to end up with just name, age, and OS, like the top right, wouldn't that? I don't see the point having a name too in there, correct?
Right, except we need it to, how to say it? So the natural join should recognize that, for example, John appears both in relation A and in relation B. So how can we find that in this table here, in the relation in the bottom?
Oh, would that be the thing that's union, isn't it? Since you get both of them in the same one, or intersection, I think.
Okay, I'll give you another hint. None of this involves the union, the intersection, or the set difference. None of those are involved.
Okay.
Okay, look at the entries, these 4 entries here in this table. Is there one entry that kind of stands out as being different somehow? different than the rest?
I guess no, I'm honestly not sure now.
Okay, here I'll highlight this one. What makes this entry different than the other three?
They have the same name.
They have the same name, right?
Right.
And the names on the left are coming from table A,
Yeah.
and the names on the right are coming from table B.
Mm-hmm.
Okay, so this yellow one shows that John appears in both table A and table B.
Okay.
You agree with that?
Yeah.
Okay, and that's the only one that's like that. So that we want to keep, because remember, we want only those entries that have that appear in both relations. So this is something we want to keep. Okay, so how can we keep only those rows that have this property?
Like specifically how, like using anything or just theoretically, or I don't
Okay,
understand like how you want me to
so
answer that.
let's see. Here we have name, age, name to OS. The result of this should be only keeping the entries where the names match. So
Right.
this would be the result. Um,
Yeah.
so what operation can I do to go from this to the one on the right?
Well, you would just check name one and name two, and if they equal the same, then you move them. Correct.
If they're the same, then you keep them. Yeah. Okay, so what operation does that? Not the union, not the set difference, not the intersection. What operation filters rows?
Select, I guess. Select by name and select by name too.
Okay, yeah. So if we do a select here, and what's the predicate? What's the yes/no question on whether we keep this row or not?
Uh, well, you would just want the name if they're equal, so it's select name. Uh,
Name equals name
double.
two.
Yeah,
Yeah. Okay, very good. Yeah, and that will result in this, right?
yeah.
Okay, very good. So I'll repeat it again, and then I want you to tell me if you're okay so far. So we cross multiply to get all of the information from both tables into one relation. So the number of columns that you have is bigger, and it includes all of the columns from A and all of the columns from B. So we're ending up with one relation that has sort of all of the dimensions of information of any of the relations. That's one part. The second part is that it does all possible pairings. So everything in A gets matched up with everything from B. And after that, we are interested in those rows that share a common attribute. In this case, it's the name attributes that should match, and so you can do a select. After you cross multiply, you eliminate all of those rows where the names don't match, or otherwise you keep only those ones where they do match. Okay with that?
Yeah, that makes sense.
Okay, very good. Thanks. How about Ali or Ali. Okay. Anum? Anum? Anum, I think. Yes, please.
Hi, Professor. How's it
Hey,
going?
good.
Yeah.
Okay. So, yeah, we're almost there. How can we get to this table?
Uh, can we try project name, age, and OS?
Would work? Yeah. So if you project name, age, and OS. Very good. So, yeah, these are the 4 operations. In particular, it's a project, a select, and a cross multiply with some rename operation. Okay, I'm leaving these things blank, what you're renaming, exactly your selection, and exactly what you're projecting. But yeah, that's it. This is a natural join. So this is the same thing as a natural join. And if you have inner joins, outer joins, left joins, right joins, whatever, I'm confident that you could sit down and come up with how to reproduce those using the lower level operations. Yeah, Mark, you still available?
Yeah.
Great. Just because you volunteered yourself, I'm going to ask you a question about the cross product.
Sure.
So this is all possible pairings, yeah? If I have a relation A with n entries, n rows, and I have a relation B with n entries, how many entries will A cross B have?
How many entries? So how many
Rows.
rows? Rows.
Sorry, rows.
Would it be just um the rows of the number of rows in table A times the number of rows in table B?
Very good. And so how many is that?
I don't know how to express it. I just know how to say it.
Okay, so the number of rows in A times the number of rows in B. Is there a simpler way to rate that? Does that work?
Would it just be n squared?
Yeah,
Okay.
n squared. Yeah, that's right. That's n squared rows. Right. So in general, if you have n rows in one and m rows in the other, then you will have n times m rows. Okay, if these are both n, then that's n squared rows. Okay, so this is to say that cross multiplication is expensive. Okay, if A has 1,000 rows and B has 1,000 rows, then A cross B is going to have like 1,000,000 rows. So it jumps up pretty quickly. And this pattern continues. If you have a third C also with n rows, and you want to cross multiply all of these together, and that's n cubed. Now, if each of those are 1,000, now you're up to 1 billion rows, right? So you have 3 columns with just 1,000 rows, but when you cross multiply them, you end up with like 1 billion rows. Okay, so cross multiplication is a expensive operation, and you can't really get around it. It's just the nature of what all possible pairings mean. There's lots of ways to pair things up. In fact, if you're familiar with the birthday paradox, that to have a greater than 50% chance for 2 people to share the same birthday, you only need 23 people before that comes up to be more than a 50% chance. Which seems paradoxical because there's 365 days in a year, and how can you have so few, 23 people? It's related to this kind of thing. It's because the number of pairs is a lot. It's just the nature of the operation. Okay, so the reason why I'm bringing up the expensiveness of cross multiplication is because the join uses it, you know? And this isn't just for fun, like, oh, sure, the join does it sort of in a shortcut way, but if you want to take a long path, you don't have to use it. It's not like that. This is the way that a natural join works. If you do a natural join, then behind the scenes, the natural join will be a sequence of these lower level operations, including the cross multiplication. So joins should also be considered expensive. And avoiding joining many things together. I know this is cross multiplication, but it would extend to joins as well. If you're trying to join many different relations together, that can quickly become a very expensive operation. So it's good to avoid if possible. It's not always possible. Okay. Are there any questions about this? No. Okay. So what I will say, again, for this class, can I explain the formula one more time? Yeah, I'll do that. But for this class, if I ask how to do a query, and this is true in relational algebra and also in SQL, if you can do it with a join, that's fine. But if you write that you're using a join in this way, you will not get full credit, despite the fact that it could work and that it's correct. Usually I'll give full credit for anything that's correct. In this case, I won't. Okay, if you use this join operator, you won't receive 0 credit, but you also will not receive full credit. In order to receive full credit, you got to do the whole thing. Okay, all of the basic operations. And this is my feeling about how to ensure that people actually know how joins work. And after this class, I'll be very comfortable that if you're using a join, you know what you're doing. So go ahead and use the join word. You will have gained that ability after this class. Okay, so let me explain the formula one more time. So first, we cross multiply.
we cross multiply, and here's the concrete example. Here. That's cross multiplying. And the reason why you do this is because you want to combine in all ways relations A and B. So relation A has some information that relation B doesn't, the age. Relation B has information about the OS that relation A doesn't. But when you cross multiply them, then the result sort of combines all of their information together into one relation. The other thing that you get from cross multiplying is you get all possible pairings. And you care about not all pairings. What you really care about are those pairings where the name values are the same. Because for those pairs, where in this case the names are the same, then that means that that's an entry that exists in A and it also exists in B. And you know that because this is a pair where both of these share the same attribute. And because those are the only pairs you care about, then you can do a select. And you can filter out only those pairs that share the attribute that you care about. Yeah, we have a rename operation here. So we rename one of the columns in B because the attribute in A that we want to also match in B, we can rename it in B or A, whichever, so that for the select, we can do something like this, that the name equals the name 2. If you said name equals name, which name are you talking about? The first one, the third one? It's unclear. But if you rename the column, then there's no ambiguity. So you rename B, cross multiply it, get this really big table with all of the information. You only want to keep those rows that have an attribute that is shared. And then after that, you project. The projection is just, maybe you don't, well, first of all, you can get rid of one of the name columns because that's going to be a repeat anyway. You know that any entry in the name 2 column is also going to be in the name column because that's what survived the select operation. So you know you can eliminate at least one of these things, maybe that one. But maybe if you don't care about the name and the age and the OS and you just want to know what are the names of the people who appear in both of these tables, then you could project maybe only the name. And then that way you would get rid of these and you can just return names. Let me go back here. Could I briefly explain project again? Project just gets rid of a column. It's just like it deletes that column, the entire column from a relation. So here in red, if I have a relation A and I can project away the column B. Maybe I don't care about the column B. Here on the left in the purple, maybe I have a relation that has name, age, and parking lot. But I don't care about the parking lot for these results. So I can project and say, of this, I only want to keep the name and the age columns. And that's the result of the project. Okay. Okay. Then, sorry, I'm just going to try to save some time. time here. Okay. Okay, I'll ask one more time. Are there any questions about these operations? Because that's it. This is, I mean, those are all of the operations for relational algebra. After this, it's just going to be given relations and how do you write a query to get a relation that you want back. Give an example of select. Yeah. Go here. So here's an example of select. Given this set, this is a Boolean, or it's called a predicate. A predicate is just a statement that evaluates to true or false. So given this set, we apply this predicate, that the second coordinate is even. If it's even, we keep it. If it's not, we eliminate it. So here, the second coordinate is even. 2 is even, so we keep it. We keep that one. For this entry, 2, 3, that is, 3 is not even, so we don't keep it. Same thing for 1 and 5. 5 is not even, so we don't keep it. Here, 3 and 4, 4 is even, so we keep it. And so, let's see here. For this relation, for this select here, this is applying that the value in the name column has to be the same as the value in the name to column. So if we look here at the first row, John and Susan are not the same name. So we don't choose that one. Here, John and John, that is the same. So we can keep that one. Then we apply the predicate, is Amy equal to Susan? No, so we don't keep that. Is Amy equal to John? No, we don't keep that. And therefore, the result of this select is this entry, where we only keep that one row. Oh, so I'm seeing this question here. Why don't you keep 2, 3 if 2 is even? Because this is that the second coordinate is even. So we're only looking at the second coordinate. So we only need to look for each of these at the second number. Okay. So the rest of this class and the rest of next class, and for probably a week or two, we're just going to be going over query examples. There's going to be about 8 of them altogether. They will get progressively harder, but the point of each of them is to demonstrate sort of a technique. The ones that we'll get through this class, I'm guessing, are going to be on the slightly easier end. At some point, I will have to give maybe a half of a lecture or a lecture on what's called like qualitative reasoning. In any case, we'll get there when we get there. For the next week or two, we're just going to be coming up with queries. And by the way, relational algebra queries are so close to SQL queries. If you can write a query in relational algebra, then you can also write a query in SQL. And some queries, despite the fact that they're simple to say in English, the query themselves can get a little complicated looking. And so that's why we're going through all of this with relational algebra. All of this will carry over to SQL, and it's a very short step from taking a relation or taking a query in relational algebra and translating it into a query in SQL. I mean, it's a very short distance between the two. Okay, but I believe that if you can write queries in relational algebra, you can write good queries in SQL as well. So let's go on and get to an example. Okay. Now, I want to say again, this here, I don't know why it does this sometimes. Sorry, it seems like I can only use one pen. Okay, this here is called a schema. Okay, every relation has a schema, and the schema is the name and type of each column. Okay, that's called the schema. Really, for these queries, you don't need to know the information. This part. Oh, sorry, I can't change my pen. But the actual entries themselves, you don't need to know it. When I write it, it's just for giving an example, basically. But we will be transitioning more and more into just this, where I don't even give you any information about what the actual entries are, because that doesn't matter for relational algebra. Relational algebra only concerns itself with the schemas. Okay, so if you know the schemas, that's good enough. But for the purposes of working through some examples, sometimes I'll give some concrete entries, but this is not necessary. Okay. 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 So I'm giving you 4 relations. You don't necessarily have to use all of them. Sometimes you will, sometimes you won't. But here's 4 relations, and I want to know what is the query that will return all restaurants frequented by at least one person under the age of 18. Okay, I'm going to give you guys 3 minutes to work on this and actually sit down and try to figure out this query. That's really the best way to start to better understand this stuff, is to actually try to go through it. So try to take the next 3 minutes and see if you can come up with a query for this. Okay, I'll check in at 12:58. Okay. Anybody think they have a guess or an answer?
I could try.
Great.
So this is a SQL query, right? Or no? Are we doing a algebra query?
Algebra.
Okay. So we would multiply the two tables by each other, the person and the frequency. No?
Okay.
Okay. We would rename the name column in frequency to name2.
Okay. Sure.
And then from the table that is made from this, we drop the name2 column.
Okay.
Or we could select where age is less than 18.
Yeah, it's better to do that first.
And then we could drop the name2 column
How do you drop the name2 column?
with the projection.
With the projection. Okay. Um, two things. One's a small thing. The project here, we want to find all restaurants. So we don't care about the other stuff. So here, we'll project only the name of the restaurants.
Right.
We don't need anything else. Okay. There's one other thing that's missing from this. I want to see if you can catch it. It has to do with the select.
Oh, we're selecting the restaurants. Also?
No? Nope,
No.
not that.
We want to do it where name equals name in both the
Very good.
tables.
Yeah. Yep. Where name equals name2. Okay. And I'm going to introduce this symbol here. You don't have to use it. Okay. So first of all, yes, that's perfect. Yep, exactly this. Perfect. Yeah. Just a quick note, notational note. Okay. For sets, we have this for a union, this for an intersection. But for Boolean operators, we have this for and this for or. Okay, so if I write a triangle, it's not a sloppy this one. I'll try to be careful. But yeah, this means and this means or. And I'm assuming you guys are familiar with some Boolean logic. 1 or 1 is 1, 0 or 1 is 1, 1 and 0 is 0, 1 and 1 is 1, whatever. Okay, so yeah, that's just a notational thing that I'll do here. Very good. Okay. Then before I go to the next example, are there any questions about this one? No? Okay. Oh, can you scroll down and see the notation? Yeah. Maybe I don't even need this about the sets. I mean, it's, well, whatever. Yeah, these are two very different areas. Sets have sizes and objects and elements, and but Boolean operators, that's about truth statements, or what are called predicates, things that evaluate either true or false. Okay, great. Let's go to example 2. Okay, and again, I don't need to put this, but I will just for fun, or just to give you guys something concrete. Yep. Okay. Find the names of all females who eat either yogurt or salad or both. Okay. So I'll do the same thing. I'll give you guys 3 minutes and see if anybody has an answer. So I'll come back at 1:08. Okay. Anybody have a query they'd like to proffer? Okay, let's spin the class wheel. And Christian.
Hi, Professor. How are you?
Doing okay. What do you think?
I
Do you
think
have any ideas?
this is a toughie, Professor.
It's a toughie. Okay.
Yeah, it's a tough one.
All right. Well, let's see how far we can get before. Let's see how far we can get. Which relations do you think are relevant to this query?
I would say that you have to find the names of all the females who would either eat yogurt salad or both. So definitely relations between person and eats, obviously.
Okay. Very good.
And you would have to use the genders as well, Amy and Jane, and find out what they eat too.
Okay. Good. So we have two relations at least. Each of these relations have something relevant to the query. How can we combine them together?
Well, you could use the union operator, I believe, right?
Okay, so let's see. If we tried to union them, how would that? Oh, sorry. Yeah. Let's take person, and eats. Okay, if we wanted to union them together, then let's see. How does that work? Okay, well, what would be the first entry in this if we union them together? So this is person, union, eats. First of all, what's the schema for this look like? Like, what are the columns?
Wouldn't it be? Oh, actually, that's wrong. Because it would be wrong because it would only be name, right?
Yeah, name is the only thing that they have in common. So,
Yeah, my bad.
Okay.
Yeah, so then you would probably need something like a I would say not interjection, set difference.
Okay, how would that work?
Well, I guess you. I think there's an easier way to do it. Would it be projection then?
What are we projecting?
You would have to take whatever does not, whatever columns are not in person, which is food, and then combine it with person.
Okay. Projection doesn't combine things. Projection just deletes a column.
Yeah, it's a real toughie, Professor.
How about a cross multiply?
That was my next answer. Yeah, cross multiply.
I'm not sure there's so many left. Yeah. Okay. Good. So let's do that. Person cross eats. Okay. And now, really quickly, we'll show what that would look like if we projected that. So here's person cross. Person cross eats. Can I add a insert right? Good. Table insert right. Okay. So what that would look like is, well, first of all, we'd take John 16 male, and we're going to pair it with everything here. So we'd get John 16 male paired with John and yogurt. Then we'd have John 16 male paired with Amy and salad. And here, sorry, let me move this. Then here we'd have name, which is text, and food, which is text. Okay, so we're pairing up John first. So John, who's 16, gets paired. Sorry, he's 16, male. First he gets paired with John, then Amy and salad, then Amy and yogurt, and then Jane and salad. And then we pair up Peter, who's 19 and male. He gets paired with John and yogurt, then Peter, 19 male, would get paired with Amy eating salad, and Peter, who's 19 male, would also get paired with Amy, who eats yogurt. And do you have the kind of idea how this would work? And I don't want to necessarily finish this. Sorry, who was I talking to?
Me.
Yes. Okay. So, are you clear on like how this would sort of go if I don't finish it?
Yep, I got it.
Okay.
So the names would line up, and then based off of that, you would have to find whatever the female entries in the gender column, and then the yogurt or salad or
Very
both
good.
in the food column.
Okay. So really quick, I'm going to do a quick rename on eats. How should I do the rename? Because there's a problem here that there's two name columns. And I'd prefer to have each column name be unique.
So you would have to use row like you said already.
Mm-hmm. I'll just do this. I'll change the name to name 2. Just because. And that would result in that. Okay, so now this column name and this column, they each have unique names. That's easier to refer to. Okay? Now you say we want females. Okay, how do we get females out of this? How do we keep only the females?
All right. Now this is the time when we would have to use one of the operators, which would be union.
Okay, what are we unioning with?
Nope, never mind. That doesn't look like it is.
Yeah, I'll tell you that there's no need for union, set difference, or intersection.
Is it natural? Yeah, it would be natural, right?
So this is akin to a natural join, yes, but we're not writing a natural join. We're doing it the long way.
All right, got you. So it's got to be select, right?
Select, okay? So we're going to be deleting certain rows from, so here's the relation that we have. And by the select, we're going to say, for example, this first row, is that, should we keep that row or get rid of it?
Get rid of it. It's male.
Get rid of it. Yeah, because it's male, right? Okay, so because it's male, so therefore gender should be female, right? If it's not female, we get rid of it. Okay, so I didn't write enough of these down, but okay, so all of those are going to be gone. Are there what is something else that we can use to get rid of the many entries in this table?
You could also use food.
Food, okay.
So anything that's not yogurt or salad.
Anything that's not yogurt or salad. Okay, so food here. Food should equal yogurt. Or food equals salad. Like that. Okay? Very good. There's one other condition.
Then you would have to do an either or, right? Because it's either salad, yogurt, or salad, or both.
This includes that. That's fine. How about this entry here? Is this gender female?
Oh yeah.
Okay. Does food equal either yogurt or salad?
Oh yeah, but no, but then you would have to if the names are not equal to each other, then we have to delete that.
Good. All right. So that's it. That's it for the select. Now, once we do that, we're going to be deleting these rows and only keeping the ones that match. But we only want to return the names of these people. So how do we do that?
Then I believe it wouldn't be a natural join. You would have to use something like at select again.
Nope, select gets rid of rows. Here we only care about the column. We only want to return the name. That's it. Everything else we throw away.
Okay, yeah, I'm stuck here. I don't know.
Okay. How about project? So project gets rid of columns. So we don't want the food column, we don't want the name to column, we don't want the gender column, we don't want the name or the age column. We only want the name. And so that's what the project does.
Yeah, that was my next answer, Professor,
Okay, yeah, sure. Okay, very good. Okay, guys, well, it's 1:20. I don't want to keep you after. We will pick up, basically the next few classes are just going to be like this. I'll be giving relations, giving a query, and seeing how we state the query. We'll be getting harder than this. So I encourage you to review and get some practice in. And have a nice Halloween, have a nice weekend, and I will see you next Tuesday, which is voting day, fellas. If you haven't voted yet, drop off your ballot. Don't mail it. It's no good anymore. Otherwise, go in person and be safe.
Thanks, Professor.
Mm-hmm.